All right, welcome everyone to section number 5. This is the chain rule, right? So we're going to upgrade, just like back in Calc 1, we had the chain rule, right? For single variable functions, we would like to upgrade and be able to talk about a chain rule for multi-variable functions. So that's what we're going to do. We're going to define the chain rule, and then we're going to introduce these things called tree diagrams, because it turns out there's actually chain rules for many different situations, and these tree diagrams help us remember them. Okay, so here is an example of kind of a real world question of why you would want a chain rule for multivariable functions, right? So here we are. Suppose a mountain's height is given by this function, right? A mountain's a nice surface, right? And we're walking along this path, right? So in this case, I have this nice red path here. This is my r of t. It's a position function, right, that we're walking along. And the question is, maybe at t equals 2, at time 2, 2 minutes, 2 hours, whatever, right? The question is, are we going up the hill or down the hill? So if we had equations for all of these things, could we tell at the specific time, are we going up the hill or down the hill? So like I mentioned, obviously we need a lot more details, right? I haven't given you what the surface equation is. I haven't told you what our position function is. But if I gave you a lot of those details, I would hope that we would be able to answer this question. And it comes down to requiring, right, the computation of what is our height right here is the z. How is that changing with respect to time at t equals 2? So this is our good old Leibniz notation here. It's telling us, right, what we're taking the derivative with respect to. So I'd like to take the derivative with respect to t, which is a little bit weird because z depends on x's and y's. There aren't any t's here. So we have to be a little bit clever here. So again, this is saying, how is z changing with respect to time, t, when t equals 2? Right? And so imagine if we're going kind of along this way in the curve and maybe time 2 is right here, then we'd probably say, well, we're going up based on this picture probably, right? We're going up, so it'd be positive, right? A positive rate of change. All right, so we want to develop a I guess let me back up here. I hope that this has maybe motivated why we would want such a thing, right? Why we want chain rules for multivariable functions. Okay, so back in Calc 1, we had something that says, right, if you want a derivative of y with respect to t, well, this is the same thing as the derivative of y with respect to x times the derivative of x with respect to t. This was the chain rule for single variable functions. So a natural upgrade, right, is that if you want the derivative of z with respect to t, then maybe this would be the derivative of z with respect to x times the derivative of x with respect to t. Or it could be that the derivative of z with respect to t could be the derivative of z with respect to y times the derivative of y with respect to t. So either way, you can kind of see, just like back here, the dx is canceled and this somehow made dy dt. Again, they don't actually really cancel. This is just notation for the derivative, but it is a nice way to remember it. So kind of, again, here the x's would cancel and you would get dz dt. Here the y's would cancel and you get dz dt. And so the question becomes, which should it be, right? We need one number, so which of these should it be? And the answer is neither. Or I mean, both. So it turns out it's actually a combination of these things here. So let me give you what it actually is. So we're going to go ahead and suppose, here's all the technicalities, right? We need a nice surface here. It's differentiable, so we can take the derivatives of it, partial derivatives, all that good stuff. And then x and y are functions of t themselves. So x is a function of t, y is a function of t, and they should be differentiable, right? We should be able to take the derivatives of them. And if all this is true, then z, that surface up here, is differentiable with respect to t. And here's the equation. So it goes, the derivative of this function, or z if you'd like, with respect to x, so this is a partial derivative, so I'm using my partials here, times dx dt, the derivative of x with respect to t. So again, kind of you see these x's sort of canceling out. That's the first one here. Then you do plus the derivative of f with respect to y times dy dt, right? The derivative of y with respect to t. So you can see actually both of these appear here. So it's neither one of these, it's actually both of them, and you add them together. Or equivalently, right, so here I use the f notations. You could do the partial of z with respect to x times dx dt plus the partial with respect to z, sorry, the partial of z with respect to y times dy dt. So you can use kind of either the f or the z, just like sometimes back in, Calc 1 or in algebra, right, y and f were kind of interchangeable. Here, the z's and the f's are kind of interchangeable as well. And let me actually, so this is, right, using the Leibniz notation here. Let me go ahead and also write down maybe with the subscript notation, right? So the partial of f with respect to x, that would be f sub x times, and now the partial of x with respect to t. Well, in this case, the only variable here that x depends on is t. So you could actually use the prime notation, but kind of a better way to go, something maybe as we expand this a little bit further, we may want to actually use the subscript notation here. So x with respect to t plus f with respect to y, right? So the derivative of f with respect to y times the derivative of y with respect to t. So this would be the subscript notation. So you can use this if you would prefer. Okay, so there's the theorem. That's how we calculate out something more complicated, a more complicated chain rule here for surfaces. So now let's get a little bit of practice applying this to a specific example here. So go ahead and calculate out dz dt, where this is our surface, and then x is a function of t, y is a function of t. I would recommend pausing the video, try to get as far as you can, give me the dz dt, and then unpause it and I'll spoil the surprise. Alright, and this is how far I got. I calculated out all of the components that we're going to need. So we're going to need the partial derivative of z with respect to x. We need the partial derivative of z with respect to y. And there they are. So 2x plus y, right? Because this one would be constant in that case. And the partial with respect to y. So let's see, this is constant. It goes away. Here this is 2y raised to the first power. Check. And the derivative of this with respect to y is just x. Likewise, I calculated out dx dt, right? The derivative of x with respect to t, its cosine, and the derivative of y with respect to t. Well, in this case, it's just e to the t. So now, according to our chain rule, we have dz dt is equal to the partial derivative of z with respect to x times the derivative of x with respect to t plus the partial derivative of z with respect to y times the derivative of y with respect to t. So let's go ahead and plug these things in. So here's my first partial, 2x plus y times dx dt, so that's cosine of t, plus the partial of z with respect to y, so in this case it's 2y plus x, times dy dt, which is e to the t. So there is my derivative of z with respect to t. Now, one kind of small subtlety here is that quite often, when you're finding out this derivative, we would like to have it in terms of t only, right? So this has x's and y's in it, but since it's a derivative with respect to t, we should be able to get it down to just t's. So that being said, I would like everywhere I see an x, I'm going to go ahead and substitute in sine t, and everywhere I see a y, I'm going to go ahead and substitute in e to the t. And that way I can simplify this down and it'll just be in terms of t's. So 2x plus y times my cosine t, again I'm just substituting in here, plus 2y plus x times e to the t. And this is quite often, as you're doing your homework and quizzes and exams and things like this, this is how you should submit your answer, right? You should get it terms in just this final variable, these t's here, so no x's and y's. All right, so there is my final answer. We will be upgrading this here shortly. This is not where we will stop for chain rules. They get more complicated. And the claim is many books, right, including ours, bring up these things called tree diagrams. Tree diagrams. To help remember this chain rule and many other chain rules. So let me go ahead and show you what one of these tree diagrams looks like. So we have z. Z is kind of the big function here. Z is our surface, and it depends on x's and y's. So I'm going to go ahead and kind of do a few branches here, and it depends on x's and y's. Okay, x depends on t. Likewise, y depends on t. So I'm going to go ahead and give them branches. X depends on t, and y depends on t. And now for each one of these branches, we're going to go ahead and imagine like it's a partial derivative or a derivative. So this is z with respect to x. So the partial of z with respect to x. This is the partial of z with respect to y. This is the derivative, right, of x with respect to t. The derivative of x with respect to t. The derivative of y with respect to t. And so the idea here is that if you would like to figure out the derivative of z with respect to t, well, you just do all of the branches that end with t's. So in this case, you go down this branch, right? So it's going to be the partial of z with respect to x, the derivative of z with respect to x times the derivative of x with respect to t, and then you add to the next branch, right? And then you multiply these together. So this is kind of a slick way to remember the chain rule, because like I said, we're going to get more complicated things, right? So imagine now, one of the upgrades we could have is that maybe you have some w is a function of x's, y's, and z's, right? So if you have a function of x, y's, and z's, what would the chain rule be? Or likewise, if your x didn't just depend on t, but maybe if x depended on s's and t's, right? It depended on two variables. Or maybe y, right? Maybe y depends on two variables or three variables or whatever, right? Maybe you have both of these. Maybe you have more. So there's a whole bunch of upgrades that we need to make, and that's what we're going to be doing in class along with some more examples. All right, I'll see you then.